every type of supernova, space is complicated. We make it simple. A supernova isn't just a star exploding. That description is too polite. It's a star briefly outshining every other star in its entire galaxy combined, releasing more energy in a few seconds than the sun will produce in its entire 10 billion year lifetime. There are several distinct ways to trigger one, and they don't just differ in size, they differ in what kind of star dies, what's left behind afterward, and in one case, what isn't left behind at all. We're going in order of how the explosion actually gets triggered. Then we'll sort them a second way by what they leave behind, because some supernovae leave a corpse and some leave absolutely nothing. Type Ia Supernovae. We begin with the strangest trigger on this list because it doesn't require a massive star at all. A type Ia supernova happens in a binary system containing a white dwarf. The dense, burnt out core left behind by a sun like star after it dies peacefully, no bigger than Earth, but packed with roughly the mass of the sun. On its own, a white dwarf is stable, quietly cooling for billions of years. But if it's locked in a close orbit with a companion star, it can slowly pull material off that neighbor, gaining mass gram by gram over millions of years. Here's the fact that changes everything. There's a hard mass limit a white dwarf can never exceed and remain stable, called the Chandrasekhar limit, at roughly 1.4 times the mass of the sun. Cross that threshold, and the white dwarf doesn't just get slightly bigger, it triggers runaway nuclear fusion throughout its entire volume almost simultaneously, and the whole star detonates in under a few seconds, leaving nothing behind at all. No core, no remnant, total annihilation. Here's the part that should genuinely bother astronomers in a good way, because white dwarfs always explode at almost exactly the same mass. Type Ia supernovae reach almost exactly the same peak brightness every single time, anywhere in the universe. That consistency turns them into what astronomers call standard candles. Since we know how bright they actually are, we can compare that to how bright they appear from Earth and calculate precise distances to galaxies billions of light years away. It was precisely this technique, applied to distant type Ia supernovae in the late 1990s, that revealed the universe's expansion is accelerating. The discovery that led directly to the concept of dark energy, arguably the biggest open mystery in all of cosmology, uncovered because a very specific kind of stellar corpse detonates with startling, reliable precision. Type II supernovae. Here's the twist. This is the classic version most people picture, and it happens to the biggest stars in the universe, the ones over about 8 times the mass of the sun. For most of its life, a massive star survives by a delicate balancing act, the outward pressure of nuclear fusion in its core pushing against the inward crush of its own gravity. That balance holds as the star fuses hydrogen into helium, then helium into carbon, and so on, up through progressively heavier elements. But iron is where the balance breaks. Fusing iron doesn't release energy, it consumes it, and the moment a massive star's core turns to iron, fusion can no longer hold gravity back. The core collapses in less than a second, falling inward at a quarter of the speed of light, crushing down until it either stabilizes as an ultra-dense neutron star, or, if the original star was massive enough, keeps collapsing all the way into a black hole. Here's the fact that should genuinely unsettle you. The outer layers of the star, still falling inward from the collapse, slam into that suddenly rigid core and violently rebound, launching a shockwave that blows the rest of the star apart in one of the most energetic events in the universe. In the process, the extreme temperatures and pressures of the explosion itself forge nearly every element heavier than iron that exists anywhere: gold, silver, uranium, all of it. Every heavy atom in your body, in your jewelry, in the ground beneath you was forged either in this kind of explosion or something closely related to it. You are quite literally assembled from the wreckage of stars that died before the sun ever formed. Type Ib and Ic Supernovae. Here's the reframe. These are close cousins of the Type II collapse, triggered by the exact same core collapse mechanism, but the star that explodes has already been stripped bare before it ever detonates. Some massive stars, particularly ones in close binary systems or those with powerful enough stellar winds, shed their outer hydrogen layer and sometimes their helium layer too, long before their core ever collapses, either blown away by their own radiation pressure or gravitationally torn off by a nearby companion star. When the core finally does collapse, the resulting explosion looks fundamentally different from a standard Type II, specifically because there's no hydrogen, and in Type IC's case, no helium either left in the outer layers to show up in the light we observe. Astronomers classify these purely by what's missing from the spectrum. Type Ib supernovae show helium but no hydrogen, and Type C supernovae show neither. Here's the fact that changes everything about this category. Some of the most extreme Type IC supernovae are directly linked to long duration gamma ray bursts, among the single most energetic explosions ever detected anywhere in the universe, so powerful that a burst pointed directly at Earth from within our own galaxy could theoretically damage the ozone layer from thousands of light years away. These particular explosions are sometimes called hypernovae, and they appear to require not just a massive stripped star, but one spinning at an extraordinary rate, focusing the explosion's energy into narrow, devastatingly powerful jets rather than releasing it in every direction evenly. Pair-Instability Supernovae. Here's the pivot. This is where the category stops looking anything like a normal explosion and starts looking like the star simply erases itself. This trigger requires an extraordinarily massive star, somewhere above about 130 times the mass of the sun, hot enough in its core that gamma rays produced, they become energetic enough to spontaneously convert into pairs of matter and antimatter particles. That conversion is the problem. Producing those particle pairs drains the very radiation pressure that was holding the star up against its own gravity, and the core begins to collapse. Here's the fact that should genuinely bother you. In most other supernovae, this kind of collapse triggers a bounce and an explosion. In a pair instability event, the collapse instead triggers a runaway burst of nuclear fusion so violent that it can, in the most extreme cases, blow the entire star apart with no remnant left behind whatsoever. No neutron star, no black hole, nothing. The star's entire mass, sometimes over 100 times that of the sun, converts directly into an outward blast of energy and scattered elements, erasing what was moments earlier one of the most massive individual objects in its galaxy. These events are vanishingly rare in the current universe because stars this massive are uncommon today, but they're believed to have been far more frequent in the early universe when the first generation of stars formed purely from primordial hydrogen and helium without any of the heavier elements later generations would inherit could grow to sizes essentially impossible for stars forming today. Failed supernovae. Here's the twist that breaks every pattern established so far. Sometimes a massive star that should explode simply doesn't. In a small but observationally confirmed number of cases, astronomers have watched a massive star's brightness begin to increase in exactly the way that precedes a Type II collapse, and then the star simply vanishes from view entirely, with no explosion, no visible remnant, no burst of light at all. The leading explanation is that in some collapsing cores, the infalling material overwhelms the rebound shockwave before it can ever launch outwards, and instead of exploding, the entire star quietly folds directly into a black hole, swallowing essentially its whole mass in near silence. One well-documented case, a red supergiant roughly 25 times the mass of the sun, was tracked for years by astronomers before simply disappearing from every subsequent observation, with only a faint infrared glow lingering afterward, consistent with the star collapsing directly into a black hole with no supernova at all. Here's the fact that should genuinely unsettle you. This may not even be a rare exception. Some models estimate that a meaningful fraction of massive stars, potentially as much as 10 to 30%, though this remains actively debated, might die exactly this way, silently, with no explosion, no fanfare, no signal to the rest of the universe that anything happened at all. It's entirely possible that some of the deaths of the most massive stars in the observable universe have gone and continue to go completely unnoticed. It's worth pausing on just how far the effects of these explosions actually reach, because a supernova's danger isn't confined to the star system where it happens. Astronomers have identified a rough danger zone, sometimes called the kill distance, within which a nearby supernova's burst of gamma rays and cosmic rays could seriously damage a planet's atmosphere. For an Earth like world, current estimates place that distance at roughly 25 to 50 light years, close enough to strip away a meaningful portion of the ozone layer and expose the surface to dramatically elevated ultraviolet radiation without ever physically touching the planet at all. Some researchers have proposed that one or more supernovae exploding within that range tens of millions of years ago left a measurable trace in Earth's own geology. A specific radioactive isotope called iron negative 60, which isn't naturally produced by any process on Earth, has been found in deep sea sediment layers and even in lunar soil samples dated to specific windows in the past that roughly align with a period of increased extinction and species turnover recorded in the fossil record. Here's the fact that should genuinely bother you. No confirmed star within that danger radius is on an imminent collapse course today, but the nearby red giant Betelgeuse, roughly 640 light years away, safely outside the kill zone, is expected to go supernova at some point in the astronomically near future, anywhere from now to 100,000 years from now. And when it does, models suggest it will briefly become bright enough to be visible in broad daylight without posing any danger to Earth at all. It will simply be, for a few weeks, the most spectacular and completely harmless supernova anyone alive has ever seen. Superluminous Supernovae. Here's the fact that closes out the list on its most extreme note. Some supernovae are simply inexplicably far brighter than physics originally predicted any explosion should be able to produce, sometimes 10 to 100 times more luminous than a standard type II or type II event, remaining visible for months rather than weeks. Several competing explanations exist, and the true cause likely varies between individual events. One leading theory involves an unusually powerful, rapidly spinning neutron star left behind by the collapse, called a magnetar, whose extraordinarily intense magnetic field injects additional energy into the expanding debris cloud long after the initial explosion, reheating and rebrightening material that should otherwise have already begun fading. Another theory suggests some of these events happen when the explosion's outward shockwave slams into an unusually dense shell of material the star had already shed in the years immediately before its death, converting the collision's kinetic energy directly into an extended burst of additional light. Here's the part that lingers. Because these events are so extraordinarily bright, they're visible across a substantially larger portion of the observable universe than ordinary supernovae, meaning some of the most distant individual stellar explosions ever detected are, almost by necessity, members of this single, still poorly understood category. The events bright enough to be seen from nearly the edge of what current telescopes can reach at all. Historical supernovae. Here's the fact that closes the loop on everything above. A handful of these explosions have happened close enough and recently enough that humans watched them happen with nothing but the naked eye, centuries before anyone understood what they were witnessing. In the year 1054, Chinese astronomers recorded a guest star suddenly appearing in the sky, bright enough to be visible in daylight for over 3 weeks and visible at night for nearly 2 years. A Type II core collapse explosion whose expanding wreckage is still visible today as the Crab Nebula, and whose leftover core is now a pulsar spinning roughly 30 times every second, discovered exactly where 900-year-old records said the explosion had occurred. In 1572, astronomer Tycho Brahe observed a new unmoving star appear suddenly in the constellation Cassiopeia, bright enough to be seen during the day, and his careful, precise measurements of its lack of parallax helped demolish the ancient belief that the heavens beyond the moon were fixed and unchanging forever, the supernova that helped end a 2,000-year-old assumption about the nature of the universe. Here's the fact that should genuinely bother you. No naked eye supernova has been observed within our own galaxy since telescopes were invented. Every supernova witnessed with proper modern instruments has been in another galaxy entirely, meaning nobody alive today has seen what Tycho or the Chinese astronomers of 1054 saw with their own unaided eyes. The closest exception came in 987 when a star in the Large Magellanic Cloud, a small satellite galaxy roughly 168,000 light years away, detonated as SN 987A, close enough that instruments on Earth detected a burst of neutrinos arriving hours before the visible light did, the particles passing almost undisturbed straight through the star's own outer layers, while the light took longer to fight its way out. It remains the closest supernova observed with modern astronomical instruments, and astronomers are still watching its expanding debris today, waiting to see whether a neutron star or a black hole eventually reveals itself at the center of the wreckage. A question that decades later still isn't fully settled. Here's a number worth sitting with before we close. Astronomers estimate that a supernova of some kind goes off somewhere in a galaxy the size of the Milky Way roughly once or twice every century, based on the observed rates across many similar galaxies and the known population of stars capable of ending this way. Given that estimate, statistically, several supernovae have likely occurred within our own galaxy since the last confirmed naked eye sighting in 1604. We simply haven't seen them because thick clouds of interstellar dust along the galaxy's spiral arms block visible light over most of its disk, hiding entire regions from direct observation. Modern astronomers instead search for the leftover radio and X ray signatures of these hidden explosions, and several candidate remnants with ages that fit the expected timeline have already been identified this way, exploded and unnoticed by anyone until instruments capable of seeing through the dust caught up centuries later. It's entirely possible that a star in our own galaxy has already died in one of the ways described on this list sometime in the last few hundred years, its light and shock wave already crossing the galaxy, and that nobody has looked in the right place with the right instrument to notice yet. Let's sort these 7 again a different way, not by trigger mechanism, but by what's left behind. On the total annihilation end, type Ia and Pair-Instability Supernovae, both capable of leaving absolutely nothing behind, the star's entire mass converted directly into light and scattered elements. On the corpse-forming end, standard type 2 Ib and Ic Supernovae, which typically leave either a dense neutron star or a black hole at their center, depending on how massive the original star was. On the silent end, failed supernovae, which skip the explosion phase entirely and simply vanish into a black hole with no visible event at all. And on the mysterious end, superluminous supernovae, whose leftover remnant and even whose full mechanism is still a genuinely open question in astrophysics. Every category on this list ends the life of a star in a fundamentally different way. Some erase it completely, some compress it into an object stranger than anything else in the universe, and at least one appears to erase the very evidence that anything dramatic happened at all. Here's the last thing worth sitting with. Every atom of iron in your blood, every atom of calcium in your bones, and every atom of oxygen in the air you're currently breathing was forged inside a star that later died in one of these ways, then scattered across the galaxy for potentially billions of years before ever becoming part of you. You are not just watching these explosions from a distance. You are made of their aftermath. Not bad for stick figures on a rock,